Bismillahirrahmanirrahim. Welcome to the second part of 18th lecture of Statistics and Probability Theory. We will continue with the topic normal distribution. Data can be dispersed in different ways. It can be spread out more on the left, like you can see in this figure that the peak of the data is on the right side and the tail is on the left side, or more on the right, as you can see that peak is at the left side and the tail is at the right side. So this one is called the positively skewed data and this one is called the negatively skewed data. And in this case it can be all jumped up. So this is the random behavior of the data. You can't say that it is positively skewed or negatively skewed. But there are many cases where the data tends to be around a central value with no bias left or right, as you have seen in previous slide, and it gets close to the normal distribution like this. That is, more concentration of the data is at the center and the curve of the data is more likely to be the bell curve, so it is close to the normal distribution. So this is the bell, and you can see that this is the as similar as the shape of the curve of the normal distribution. It is often called a bell curve because it looks like a bell, like this. It looks like a bell, and many things closely follow a normal distribution, like heights of people, size of things produced by machines, errors in measurements, blood pressure, marks on a test. Many more real life phenomena are there which follow the normal distribution, and this normal distribution is very useful, or you can say it is very necessary in the inferential statistics. We say that data is normally distributed if the normal distribution has the following properties. As we have discussed this in previous part also, just for the sake of the revision, mean should be equal to median and is equal to mod. All these measure of tendency, central tendency, should be equal, that is at the center of the data, and symmetry about the center. 50% of values less than the mean and 50% of the values greater than the mean, as we know that the normal distribution is bell-shaped and its mean, median and mod lies at the center or at the peak right over here. So 50% data should at the left side or less than the mean, and 50% data should be at the right side of the mean, or you can say that 0.5 should be here and 0.5 should be here, as you know that this is probability density function and total area under the curve should be equal to 1. All odd order moments are 0. As you know that moments is the sum of the deviations for which we take a power and we take their average. We have discussed in the previous classes They are usually denoted by M1. These are the sample moments. M2, M3 and M4, and these are, let's say, these are the mean moments, or you can say the central moments. We have already discussed these moments in previous classes, and M1, M2, M3, M4. So they are saying all the odd order moments are 0. So this M1 and M3 will be 0 in the case of normal distribution. This is the example for understanding the concept of mean and standard deviation in normal distribution. As we know that normal distribution has two parameters, mean and standard deviation, or you can say mean and variance. And these are two curves. This is the curve A and this is the curve B. As you can see that curve A has the higher peak than the curve B. The peak of the curve B is flattened and the more tendency is at the tails, whereas in curve A the peak is the higher. So they are asking which curve has the greater mean. Curve A has the greater mean. The line of symmetry of curve A occurs at 15 and the line of symmetry at curve B occurs at 12. So this is the line of symmetry. Here x is equal to 15 and this is the line of symmetry for the curve B, and this is the line of symmetry for the curve B. So 15 is greater than 12, so it has the greater mean. Which curve has the greater standard deviation? Curve B has the greater standard deviation. As you can see the spread of the curves, curve B has the larger spread than curve A. So the curve B has the greater standard deviation. As you know the definition of the standard deviation, that is it is the measure of dispersion, and the definition of measure of dispersion is the how much the data is dispersed around the mean. So this one is the mean for the curve B, and this one is the mean for the curve A. And if we change the color, so this is the spread of curve A, and if we change the color for the curve B, and this one is the spread for the curve B. So you can see that this space or this area is larger than this curve A. So obviously it has the greater standard deviation, as standard deviation is the measure of dispersion, and measure of dispersion tells us that how much your data is dispersed around your mean. Probability density function. A continuous random variable x is said to have a normal distribution with parameters mu and sigma, where mu this is the range of the parameter mu, which is from minus infinity to infinity, and standard deviation should be greater than 0 if the probability density function of x is, so this is basically the probability density function of x depending on the parameter mu, and sigma, where sigma is the standard deviation, 1 over under root 2 pi sigma. This sigma is outside this under root, e raised to power minus x minus mu whole square over 2 sigma square, where this is the range of the random variable x, which is from minus infinity to infinity. If you write in the shorthand notation, x follows the normal distribution with mean mu and variance sigma square. So this is the way to write out that this random variable is following the normal distribution with the parameter mu and sigma square, you can write it for the other distribution as well, that if x is following the binomial, so you can write it in this way: x follows binomial with parameter n and p. Likewise, you can write it for Poisson distribution. X is following Poisson this is the shorthand notation with parameter lambda into t, or you can write it for the Bernoulli. For the Bernoulli trials, it has one parameter, p. So this is the way to write out the shorthand notation that your random variable is following a specific distribution with obviously the distribution should have the parameters. Z-scores. So Z-score is basically the x minus mu over sigma. You are transforming this random variable x, these scores, into the Z-scores x minus the mean of the distribution, which is mu, divided by the standard deviation. So now you have this new random variable, which is z, and you can say it Z-scores. Now what will happen here when you subtract the mean from the random way, this Z-scores, and divided by the standard deviation? So when you do it, let me change the color of the ink. So by taking the, as you know that this x is following the normal distribution with this parameters mu and sigma. So what will be the parameters, or you can say mean and standard deviation for this Z-scores or this Z? By taking expectation on both sides, you will get expected value of Z, which will be equal to expected value of x. No, this is not a good one. Let me erase this. Right, fine. Now this is x minus mu over sigma. So as expectations applied to the variable, so it would be expected value of x, as mu and sigma are constant, so it would be equal to mu and divided by sigma. As you know that expected value of x is basically the mean of the variable, and this random variable is following the normal distribution and its mean is mu. So here we will have expected value of x will be mu minus mu over sigma, which is obviously equal to 0. So the expected value of z, or you can say the mean of this random variable z, will be equal to 0. Now what would be the variance? As variance is the second parameter, variance of z is equal to variance of x minus mu over sigma. as we have already studied the properties of the variance in the chapter measure of dispersion, so by applying it you will get variance of x over sigma square. Now, variance of x, as you know, this x is following the random normal distribution with mean mu and standard deviation sigma or variance sigma square. So, variance of x would be equal to sigma square over sigma square, which will equal to 1. So, now this random variable has mean 0 and variance or standard deviation 1. So what will be the distribution for this? This will be standard normal distribution. A normal distribution with a mean of 0 and a standard deviation of 1 is standard normal distribution. So this Z will have, if we write it in shorthand notation, standard normal distribution with parameter mean 0 and variance, or you can say standard deviation 1. So this is the random variable Z, which is following the standard normal distribution. Now you can see here we have the z-scores and total area under the curve is 1 and mean of this distribution is, this normal distribution is 0 and this total spread is 1. Now, a continuous random variable x is said to have a normal distribution with parameters mu and sigma with PDF, this as we have studied in previous slide. Now, as we have converted this x into z, which we called the z-score, now the normal distribution with parameter values mu is equal to 0 and sigma is equal to 1 is called a standard normal distribution. The random variable is denoted by z, as we have seen here. This is z and we have converted it into standard, we have converted it into z-scores, and this z random variable has the mean 0 and variance 1. Now this is standard normal distribution, and what will be its PDF? Here you know that z is equal to x, this should be small x minus mu over sigma. So if you see this part, x minus mu whole square over 2 sigma square, so this will be equal to z square over 2, this 2 will come here over 1 over under root 2 pi, and you know that sigma is equal to 1 as this is standard normal distribution. So this is the PDF of the random variable x, and this is the PDF of the random variable z, which have mean 0 and variance, or you can say the standard deviation equal to 1, which is now we call the standard normal distribution.